All right, let's dive in. You sent over some research on ant trails,
Yeah.
and it got me thinking about how these little creatures can, like, self-organize.
Hmm.
It's pretty wild, without any, like, central command. They managed to do some really impressive stuff.
It is pretty amazing.
So how did they pull it off? What's the secret?
Well, that's what this study dives into. They used a simulation
Okay.
with like digital ants searching for food in this virtual world.
Ah,
And
interesting.
the cool thing is, even with this simplified setup, it still matches how real ants behave surprisingly well.
Okay, so paint me a picture.
Right.
What's going on in this ant simulation?
Yeah.
What are they finding out?
Well, you've got these digital ants, right? They're running around looking for food, just like real ants do.
Gotcha.
And when they find some tasty morsel, they drop these virtual pheromones on their way back to the nest.
It's like they're leaving a trail of breadcrumbs for their buddies.
Exactly.
But where's the big reveal, the aha moment in all this?
The aha moment comes when you throw in two food sources.
Okay.
At first, the ants kind of spread out, exploring both options.
Makes sense.
They leave trails to each source. But here's the kicker. If one source is even a little bit closer to the nest,
Hmm.
that's where things get interesting.
All right, you've got my attention. What happens? What's this interesting part?
Okay, so that closer food source,
Yeah.
just by pure chance, it ends up getting a bit more ant traffic early on.
Okay.
More traffic means more pheromones.
Makes sense.
And then bam, you get this feedback loop. The stronger the trail, the more attractive it becomes to other ants.
So it's kind of like a popularity contest where the early leader ends up running away with the whole show.
Precisely. It's called the winner-take-all phenomenon.
Oh, I like that.
And get this, the trail to the farther food source, it just fades away.
Wow.
The whole colony focuses its energy on the winner, even if the difference in distance is tiny.
No way.
Yeah.
So, like, a small advantage can snowball into total domination.
Yeah. Pretty wild, right?
That's insane. But wait, this isn't just an ant thing, right?
Absolutely not. This winner-take-all dynamic, it pops up everywhere.
Really?
Think about how neurons grow.
Okay.
One projection wins out, it becomes the main axon, and all the others get pruned away.
Wow.
Or gene regulation. One protein ends up dominating, and it suppresses all its competitors.
Hold on. So we're seeing the same principle at work in our own brains and bodies. That's crazy.
Exactly. This seemingly basic ant study, it gives us a whole new lens for understanding these complex systems,
Right.
from the microscopic all the way to the macroscopic.
Mind officially blown. But let's circle back to these ants for a sec. I'm curious, what else did the researchers find out with this model?
Well, one of the really cool things they discovered was how certain factors can determine whether those trails even form in the first place, like the rate at which the pheromones spread, how much the ants deposit, how quickly they break down. It's a delicate balance.
So it's like a recipe. You need the right ingredients in the right amounts for the magic to happen.
That's a great way to put it.
Cool.
Like, let's say the pheromones diffuse too fast. You won't get a clear gradient.
Right.
The trail just kind of disappears. No clear trail, no efficient foraging.
Like trying to draw a path with disappearing ink.
Exactly. And then there's the opposite problem.
Okay.
If the ants aren't dropping enough pheromones, or if those pheromones break down too quickly, the trail might form but then vanish before other ants can find it and reinforce it. The signal's just too weak.
Ah, so it's all about finding that sweet spot, right? That balance between the strength of the signal and what's going on in the environment.
You got it. It really shows how adaptable these systems are
Yeah.
and how they've evolved these elegant strategies to make their foraging as efficient as possible.
This is fascinating. But I'm curious, how do they actually measure all of this? Like, how do you even go about quantifying something as complex as ant behavior?
That's where the beauty of mathematical modeling comes in. They took those basic rules we've been talking about and turned them into mathematical equations. It let them really analyze the system in a precise way. And that's what led to some even more surprising discoveries about how these simple rules can create such sophisticated behavior.
Okay, now you've really got me hooked. Let's dive into those mathematical insights.
Let's do it. Yeah, it's like cracking a code, you know?
Totally.
They took those simple behaviors we talked about, the ants walking around, dropping pheromones, following the strongest sense, and basically translated all that into math. And that let them really play around with the system, see what happens when you tweak things.
Okay, I'm with you on the cracking the code part. Math, not so much.
Yeah.
Can you break it down for me? What did this mathematical deep dive actually uncover?
Okay, imagine this, right? The pheromone trail is like a river,
Okay.
and the ants are little boats navigating those currents. The strength of that's like the concentration of pheromones.
I can picture that.
So the math helped them figure out the flow rate of that river,
Okay.
like how fast it spreads out, how quickly it evaporates.
So if the flow is too fast, the trail basically washes away before other ants can follow.
Exactly. No clear path, just a faint scent that gets lost.
Right.
But then if the flow's too slow,
Yeah.
the trail might stick around, but it's not strong enough to attract ants from farther away.
So there's this sweet spot for pheromone flow then.
Yeah,
Not too fast, not too slow. Just right for those trails to form.
exactly. Like Goldilocks.
Uh-huh.
But here's where it gets even cooler. Remember that winner-take-all thing we were talking about?
Yeah.
Well, the math showed that even tiny differences in the beginning, like in those pheromone levels, can get amplified over time. Imagine one part of that river having a slightly stronger current.
Oh, interesting.
It's like a ripple effect, right? A small advantage early on can lead to this cascade of ants all following that same path. It becomes the dominant trail, precisely. It's a system that reinforces itself. The rich get richer, basically. And the math actually let the researchers pinpoint how those subtle differences in pheromone stuff could lead to big changes in how the whole colony acts.
That's wild. It's like they've mapped out these invisible forces that are shaping these ant highways. But it makes me think, what happens if those highways get blocked?
Oh, yeah.
Like what if a food source dries up or a predator shows up? Do the ants just keep following those old trails,
Yeah.
even if it leads to nothing?
Well, that's where things get even more interesting. It shows how sophisticated these systems really are.
Okay, so these ants have built these super highways,
Mm-hmm.
all carefully laid out with pheromone trails.
Yeah.
But what if something changes? Like what if a storm comes in and wipes out a food source?
Uh-huh.
Or a predator shows up right on their path? Do they just blindly follow those old trails, even if it leads them into danger?
Well, not exactly. Remember, these little guys are adaptable. They're
Right.
always checking out their surroundings, and if that pheromone signal starts to fade,
Yeah.
they're not just going to march along like robots.
So they're not just passive followers. They're actually thinking on their feet.
Precisely. They might start exploring new areas,
Okay.
branching out to find new food sources or maybe a different route to get where they're going. In fact, some research even suggests that they might have a way to let each other know if a trail is no good anymore.
Whoa, hold on. Really?
Yeah.
How do they do that? Like, do they have little ant megaphones or something?
Haha. Not quite megaphones, but they do have their own way of communicating with chemicals.
Okay.
There's some evidence that certain types of ants can actually lay down repellent pheromones.
Repellent pheromone.
Yeah, it's basically like marking a spot to avoid, like a danger road closed sign, but for ants.
That's so cool.
Yeah.
This whole conversation has got me wondering, though. Are there, like, lessons we can learn from these adaptable ants? Could we use their strategies to make our own complex systems better?
That's a great question, and it's something researchers are looking into. Imagine applying those principles to traffic in a big city. If we could create a system where cars could adjust their routes on the fly based on traffic jams or accidents, we could potentially make things run a lot smoother.
Whoa, so we could have self-organizing traffic, just like these ant trails. That's insane.
It's a fascinating idea.
It is, but I do have to ask, are there limits to what we can learn from ants?
Yeah.
I mean, their brains are, well, pretty tiny.
You're right, there are limits to any analogy. But even with their tiny brains, ants show us just how powerful decentralized systems can be, how collective intelligence can emerge from these really simple rules.
Yeah, it's like they're proving that you don't need some big boss ant calling all the shots to create these amazing feats of coordination.
Exactly. And that's a really important insight, one that has implications for how we design things, from AI to how organizations are structured.
I've got to admit, I came into this deep dive thinking it was going to be all about ants walking in a line. But it's turned into this incredible journey. We've talked about complexity, adaptation, and the power of nature's designs. It's really mind-blowing stuff.
Yeah, absolutely. And who knows what other secrets these little creatures are hiding. There's still so much we don't know, but each new discovery helps us better understand this intricate web of life that connects us all.
Well said. A huge thanks to you for taking us on this fascinating adventure. And to our listeners, keep those curious minds buzzing. Keep exploring the wonders of our world, big and small.